Study about FTIR spectroscopy, which stands for Fourier transform infrared spectroscopy. It is a preferred method of infrared spectroscopy. In infrared spectroscopy, IR radiation is passed to a sample. Some of the infrared radiation is absorbed by the sample and some of it passed through, or these are transmitted. We have previously studied the simple IR spectrophotometry dispersive technique. And in that technique, the resulting spectrum, it represents the molecular absorption and transmission, creating a molecular fingerprint of the sample. So spectrum that is formed in IR spectroscopy, it is the fingerprint for the molecule. Each molecule has unique type of IR spectrum. Fourier transform infrared spectrometry was developed in order to overcome the limitation encountered with dispersive infrared instruments, which we have previously studied. The main difficulty in the dispersive infrared instrument was slow scanning process. A large time was required for scanning of spectra. A method for measuring all the infrared frequencies simultaneously rather than individually was needed. So it can be measured in short time. And this solution was developed, which employed a very simple or optical device called interferometer. So through this optical device, which is called interferometer, the IR spectra can be scanned in short time. This interferometer produces a unique type of signal which has all of the infrared frequencies encoded into it. So this unique type of spectrum is also produced through interferometer. Fourier transform infrared spectroscopy is preferred over dispersive or filter method of infrared spectral analysis for several reasons. It is non-destructive technique, means sample will not be destroyed. It provides a precise measurement method which required no external calibration, and there is high speed, and the spectra can be scanned quickly. It can increase sensitivity. It is a highly sensitive method. It has greater optical throughput. It has high light gathering property. It is mechanically simple with only one moving part. FTIR spectrometer offer high sensitivity, resolution, and speed of data acquisition. All wavelengths are detected and measured simultaneously. In the short time, all the wavelengths can be detected and measured. Spectra can be scanned in very short time, and it uses an instrument interferometer, which is also called Michelson interferometer. And in the interferometer, the type of signals that are formed, that signals are called interferogram. And this interferogram is decoded by a mathematical operation, Fourier transformation. Fourier transform is a mathematical calculation which is performed on this interferogram, and then it is after this mathematical this mathematical operation, the interferogram is converted into FTIR spectra, which is a fingerprint for each type of molecule. In FTIR spectroscopy, the signals can be measured very quickly, usually on the order of 1 second or so. We can scan the spectrum in very short time. Thus, the time element per sample is reduced to a matter of few seconds rather than several minutes. In dispersive instrument, the several minutes are required for spectral scanning, while only few seconds are required in FTIR instruments. In FTIR instruments, we know that interferometers are used which produce the interferogram signals in the form of interferogram, and mathematical operation is performed on interferogram then the signals are converted into FTIR signals. Most interferometers employ a beam splitter. This is a construction of interferometer. There is a beam splitter. What is the function of beam splitter in interferometer? It takes the incoming infrared beam and divide into two optical beams. So one beam is divided into two optical beams. One beam reflects off a flat mirror which is fixed in a place. There are two mirrors. One is the fixed mirror. One is the fixed mirror and second one is the moving mirror. So the beam splitter, we divide the beam into two optical beams. One optical beam will fall on the fixed flat mirror and the second optical beam will fall on the moving mirror. Moving mirror move a very short distance, typically a few millimeters away from the beam splitter. For example, this is the beam splitter and this is the moving mirror. Moving mirror move forward and backward through a very small distance in the order of millimeter. We will see later in the diagram the two types of mirrors. The two beam reflect off of their respective mirrors, means both of the beams are reflected from the mirrors. One beam is reflected from the moving mirror and the other beam is reflected from the stationary mirror, and these beams are recombined. When these beams are recombined, when they come back at the beam splitter, because the path that one beam travel is a fixed length and the other is constantly changing as its mirror move, because one mirror is moving and the other is stationary. So the path of the beam which fall on the stationary mirror, this path length is fixed, but the beam which fall on the moving mirror, the path length of that beam is continuously changing. When both of the beams are reflected from the two mirrors, they meet at the beam splitter. So interference takes place, constructive and destructive interference takes place. The signal which exists in the interferometer is the result of these two beams interfering with each other. So an interferogram will be formed. The resulting signal is called an interferogram, which has unique property that every data point, a function of the moving mirror position which make up the signal, has information about every infrared frequency which comes from the source. Every data point which is present in the interferogram, every data point has the information about the frequency of infrared radiation which is coming from the source. So this one is a mirror. Light radiation is this is a IR radiation source. The radiation is reflected from this mirror, and the radiation also come from here, and this radiation fall on the beam splitter. Beam splitter will divide the beam into two equivalent beams. This one is the moving mirror and this one is the fixed mirror. So one beam will go towards fixed mirror and the other beam will go towards moving mirror. This moving mirror covers the distance x, mean it move to and fro from the beam splitter. When both of the mirrors reflect the radiation, these radiation then again join at the beam splitter and interference take place, and this will go through a series of mirror and through a lens on detector, and detector will detect the signals and interferogram will be formed. This is also another diagram for interferometer. A radiation from light source is reflected through a mirror, and here is a beam splitter. One beam will fall on the moving mirror, fixed mirror, and the other part of the beam will fall on the moving mirror. And the radiation after reflection come back towards the beam splitter. Here the radiation come back towards the beam splitter, interference takes place, and the radiation through the series of mirror. This is a sample chamber. Sample is placed here, so radiation will be absorbed in the sample, and here is the detector. The detector will detect the signals, and interferogram will be formed. This means that as the interferogram is measured, all frequencies are being measured simultaneously, meaning all frequencies of IR radiations are measured simultaneously, and thus the use of interferometer results in extremely fast measurement. Mean at the same time all the frequencies are measured and interferogram is formed. Because the analysts require a frequency spectrum, a plot of the intensity at each individual frequency in order to make an identification, the measured interferogram signal cannot be interpreted directly. Means we have to convert it into signals. We have to decode the interferogram. We cannot directly use the interferogram for interpretation of data about the molecules, about the compounds. So decoding is done, and decoding is done. The decoding of the individual frequencies is required, and this can be done by a well-known mathematical technique which is called Fourier transformation. This transformation is performed on the signals by the computer and then presents the user with the desired spectral information for analysis. So spectrum is formed in the desired form after Fourier transformation of interferogram. The first one is interferogram, which is formed from interferometer, and the time is on x-axis and detector signal is on y-axis, and no useful information we can get about the molecule from this interferogram. So mathematical operation is performed on this interferogram by use of computer, and this interferogram is converted into FTIR spectrum, in which these peaks are obtained, and each peak is for specific type of functional group. And this whole spectrum is the fingerprint of the molecule. We can get information about the functional groups. We can identify the molecules. Wave number is on x-axis and transmittance is on y-axis in this FTIR spectrum.